Hello again. This is Math 2232, coming to you from the College Data page, and the title of this lecture is Applications of Integrals to Probability. As always, be attentive while watching these videos. By way of introduction, this video begins our discussion of applications of integration by talking about probability and statistics applications. Now, the goal is not to teach you all of this probability and statistics course like other courses that you might take. What we're trying to do here is show you that much of what you have learned so far in this calculus course applies directly to this discipline of probability and statistics, and in a very meaningful way. You should be able to follow and complete the calculations in these examples, as well as complete the LSA2, which is based on some of these concepts. Before actually getting into the application, let's put a couple of definitions in play. So suppose that we wanted to look at the age of a person, the height of a person, the amount of time spent waiting in line, or perhaps the lifetime of a battery. Each of these quantities will have values that range over an interval of real numbers. Because of this, these are called continuous random variables. Continuous random variables are often denoted by capital X. So for every continuous random variable X has a probability density function, f of x. Probability density functions satisfy two conditions. The f of x is bigger than or equal to 0 for all x, and the improper integral from minus infinity to infinity of f of x dx is equal to 1. Probability density functions can be used to determine the probability that continuous random variables lie between two values, say a and b. This probability is denoted this way in red. The probability of a less than or equal to x less than or equal to b, that is, x lies in between a and b, is given by p of a less than or equal to x less than or equal to b is equal to the definite integral from a to b of f of x dx. This is the real definition of the density function, and this means it's a reasonable density function. Let's begin with an example then. So let f of x equal x cubed over 5,000 times the whole of 10 minus x for 0 less than or equal to x less than or equal to 10, and f of x equals 0 for all other values of x. So answer three questions. Number one, you should test and show that f of x is the probability density function. Then, question B, I'm asking that you find the probability that x is between 1 and 4. And then C, find the probability that x is greater than or equal to 6. You know what to do. Let's see how you did. Well, to show that f of x is a probability density function, we just have to conclude that it is bigger than or equal to 0. Now note that the range, if you look at x cubed over 5,010 minus x for x between 0 and 10 is clearly positive, and outside of the range we would find it to be 0. So we know that it is non-negative, so that's the first condition. And then we have to show that the probability density function is, when we integrate it from minus infinity to infinity of fx dx, is equal to 1. Let's perform that calculation. So the integral from minus infinity to infinity, we break this into pieces, but the only places where it is not 0 is between 0 and 10. So we're really integrating between 0 and 10 this function. We add 1 to the, we distribute and add 1 to the exponent and divide by the new exponent, and we get this expression, and we plug in the points 10 and 0 and do the calculation, and you should get 1. Note that we did change the limits on the integral because that's the only place where it's non-zero. So we're finished with that. Let's move to problem B, where we're supposed to find the probability that this x, given by this density function, lies between 1 and 4. And so we integrate from, in this case, 1 to 4, and it is equal to x cubed over 5,010 minus x, and then times dx. Again, we integrate, but this time we're evaluating this at 1 and 4 using the fundamental theorem of calculus. We do the calculation and we get that this is equal to 0.08658. That means the probability that x is between there is just a little bit under 8.7%, and here I'm rounding it off to the thousandth of a percent, which is actually what we normally will do with probabilities. Last, on this example, you find the probability that x is bigger than or equal to 6. So that means that the same thing is probability of x being between 6 and 10 because it's 0 otherwise. And so this is equal to the integral from 6 to 10 of the density function. Again, we raise the exponents by 1 and divide by the new exponent. And we substitute in 6 and 10. Do the calculation, we get this. And this is just a little bit less than 2/3. This is the example rounded off to the point where we're going to round it off, the thousandth of a percent. Another concept. Probability density functions can also be used to determine the mean or average of a continuous random variable. The mean is given by, this is the Greek letter mu, which stands for the population mean. Mu is equal to the integral from minus infinity to infinity, but this is x times f of x dx. Here's a different function. It has been determined the probability density function for the time that you wait in a line at a counter is given by f of t is equal to, it is 0 if t is less than 0. You never wait less than 0 amount of times. But if t is bigger than or equal to 0, f of t is 0.1 e to the minus t over 10, where t is the number of minutes spent waiting in line. So we want to answer each of the following questions about this probability density function. And in fact, I've claimed it's a probability density function, but A, again, I'm asking you verify that this is in fact a probability density function. B, determine the probability that a person will wait in line for at least 6 minutes. And C, determine the mean or average wait time in the line. You should know what to do. Let's see how you did. Okay, first we have to verify this is a probability distribution. If we look at this, it's 0 for here, and this is always a positive number, although it can get very tiny. And so this is always greater than or equal to 0. And now we have to show that the integral from minus infinity to infinity is 1. Now, since it's 0 from minus infinity up to 0, we're really just integrating from 0 to infinity. This is 0.1 e to the minus 10t dt. And as we learned, this is the limit. As the top limit tends to infinity, and of e, and we do the integration, and this is minus e to the minus t over 10, and we're evaluating that at this value a, and we're letting the limit as a goes to infinity, and 0. Now we learned how to do this when we're thinking about improper integrals, and so we'll do that evaluation, and we get that this is 1 minus e to the minus a over t, and the limit as a goes to infinity. This is e to the minus a over 10. That's in the denominator, so that goes to 0, so this is 1. So this is a probability density function. Part B, we were to determine the probability the person will wait in line for at least 6 minutes. So here, at least 6 means x is greater than or equal to 6. So we do that. So we're going from 6 to infinity of 0.1. That's 1 over 10 e to the minus t over 10 dt. That's the limit as this variable tends to infinity, and we go from 6 to that. We again have the same conditions, but we're now plugging in different numbers. And so here what happens is we're going to end up with this as this limit goes to infinity. This goes to 0, or excuse me, that one goes to 0. And so you're going to have that it is going to be a little bit better than 54%. And this is the answer where we will round it off to this level. Last thing we're trying to do is we're find the mean wait time. And so we're going to be integrating from minus infinity to infinity t, f of t dt. There's the t times f of t. And now we have to integrate by parts, which is another thing we studied. So we integrate this by parts. Make sure you are following this calculation. So this is the limit as u tends to infinity. This is parentheses minus, is minus parentheses t plus 10 e to the minus t over 10, evaluated at u and 0. We plug in and take the limit. When we take the limit as n tends to infinity, what will happen as u tends to infinity, this part will go to 0, and so you will just get 10. So the average wait time for this one is 10 minutes. Another statistical constant, the variance, and this is the Greek letter sigma, and we're squaring it. So the variance is sigma squared of a probability density function is a number that measures the spread of the probability density function f of x. How variable is it? So, and it's what is the variability away from the mean? So this is going to be sigma squared is equal to the improper integral from minus infinity to infinity of x minus mu whole squared. That's the distance from the mean, f of x dx. So, and I say or, and this is another form for this, sigma squared could also be the improper integral from minus infinity to infinity of x squared f of x dx, all of this minus mu squared. There are two formulas for this, and we'll look back on that in a minute. Now, this is called the variance. This is sigma squared, but the standard deviation, sigma, of a probability density function is a better measurement of spread, because if we're measuring things in inches, then the variance will come out in inches squared, and we want this to be come out in inches, the same thing. So this is going to be, the definition is that the standard deviation is the principal square root of the variance. And again, that's always going to be bigger than or equal to 0. So here is a definition, and here is an example. I want you to find the standard deviation for this distribution. F of x is equal to 3 over 32 parentheses 4 minus x squared, the whole of that, from minus 2 to 2, and it's 0 otherwise. Find the standard deviation. Okay, so you should know what to do. Let's see how you did. Okay, well, you see the definition involves the mean, so first let's find the mean. So mu is equal to the integral from minus 2 to 2 of 3 over 32. We multiply by x, and so this is x times f of x dx. We distribute, getting this, and we pull the 3 over 32 out, and we're going to evaluate this integral. But notice that this is an odd integral. The integrand is odd. This is an odd function, and this is another odd function. That means that f of minus x is equal to minus f of x. And as you learned in Calculus 1, when you integrate from minus a to a, an odd function, you're always going to get 0. Or you could just compute this, but you are going to get 0 for this. So mu is equal to 0. That means we can go and actually do the calculation. So the variance, sigma squared, is equal to the integral from minus 2 to 2. Now this is going to be x minus mu whole squared. But x minus mu whole squared, mu is 0, so x minus mu is just going to be x squared times f of x, which is 3 over 32, 4 minus x squared dx. So we're going to do the calculation. We're going to pull the constant out, distribute the x squared, and we get this. Now, again, remembering some of our calculus 1, we're integrating an even function because both of these exponents are even. And when we integrate an even function from minus 2 to 2, or from minus a to a, what will happen is that is twice the integral from 0 to, in this case, 2. Now, the reason that's convenient is because plugging in 0 is very easy after I integrate this. So I'm using the fact that this is an even function to do this simplification of 2. Now 2 times this is 2 times 3 over 16 is 2 times 3 over 32 rather is 3 over 16. I add 1 to the exponent in each case and divide by the new exponent, and I get this. And when I plug in the bottom number, I get 0. But when I plug in the top number, I get this. And continuing the calculation, because I can factor out 32. See, 4 times 8 is 32, and this is 1 over 5 times 32. So I can factor out the 32, and I'm left with this, and that is 1/3 minus 1/5. And so this is going to be 6 times 2 over 15, which is 4 over 5. Now don't forget that what we were calculating here was sigma squared, so we need to take the square root of sigma squared. So sigma squared was 4 over 5. That means that sigma is equal to the principal square root. So that's going to be 2 over the square root of 5. There's nothing wrong with this. This is okay, but sometimes teachers wanted you to rationalize it. This is rationalizing it. So this is the exact standard deviation. Now earlier I said that the formula could be this or this, and now I'm asking why. So in other words, what I'm asking you to do is take this and show that it's also equal to this. You know what to do. Let's see how you did. Okay, let's just start on this side then. And so here's the definition. But now what I'm going to do is I'm going to do algebra, and so I'm going to square this. So when I FOIL this, I will get x squared minus 2x mu plus mu squared times f of x. And then I'll break this into 3 integrals. So it's going to be this minus 2x mu f of x dx, and this is going to be mu squared f of x dx. Now, mu squared is a number, and so I can pull out mu squared here. It's a constant. It's what's the average value. So I can pull this out, and then I have the integral from minus infinity to infinity of f of x, which we know is 1 because that was a probability distribution. And so that is 1. When I look at this term, and actually you could do this 2 ways. One way, which is not the way I'm showing it here, but you could say that 2 mu is a constant, and so you could pull out 2 mu in front, and then what you would have left is x f of x dx, which is going to be minus 2, and that's going to be the mean, or that's going to be 2 mu, but then the integral of x dx is going to be mu again, so that is going to be minus 2 mu squared. So you see you get mu squared from this, minus 2 mu squared from this, and so this is going to be, those will become minus mu squared, and this will become just what I show here, minus infinity to infinity x squared f of x dx. Now, another way you could have done this, and in fact what I'm really showing here, I talked through what I think might be an easier way, but you could actually do integration by parts. You could let u, in this case, be minus 2 mu, and that means dv, it's everything else, is x, f of x dx. And so this is going to be then, and mu was this integral. So when I integrate v is just going to be mu. And so when I do that, I'm going to get the same result. My students generally like this formula better when I teach them statistics. Now, we are going to talk before we finish up here about normal distributions because they're very important in many of the sciences. And these are, in fact, the things that you've talked about many times called bell-shaped curves. So here's an example of several bell-shaped curves, and here is one of them. Now, it's important that you realize that a normal curve really depends on only two parameters. It depends on the mean, what's the middle value, and it also depends on how is it spread, the standard deviation. So normal mu sigma, that makes that every normal distribution depends only on the mean, and sigma, we call that a two-parameter family, and it's completely determined by these values and the fact that it is a normal distribution. Now, the normal distributions then are shifted because the mean shifts where the middle is, and you can see that shifting here. And sigma says how spread out is the distribution. So you can see that the red distribution isn't spread out nearly as much as the green distribution and as the, I guess I'm going to call that aqua distribution here, which is spread out quite a bit. So the variance and the standard deviation tell you the spread. This tells you where is the center. Now, a random variable then, it only depends on these two things, and that's true. But a random variable x is said to have a normal distribution with mean mu and standard deviation sigma whenever this is the density function. Now this is quite complicated, but you see this actually is a constant here that makes the area under the curve from minus infinity to infinity 1. So the constant in this case is going to be 1 over sigma, the square root of 2 pi. Now it ends up being a calculus 3 thing before I could show you this, but I'm really just trying to give you an idea. So this is the constant, and so it is this constant times e to the minus 1 over 2 sigma squared, and this is x minus mu whole squared. Now the only thing that's a variable here is the x. The rest of this is a constant. This says what is the mean, and this is the standard deviation, and this forces the integral to be 1. And so the graph of this looks like this, and that is a normal probability density function. Now notice that fundamentally, except for the constants, this is f of x is equal to e to the minus x squared, or minus u squared. Remember that we cannot integrate this. We have to do approximate integration or numerical integration for this. So pay attention to that as we go forward. Now this actually is what's used a lot in statistics, and we have a thing called the empirical rule. And the empirical rule says for any normal distribution, there are a little bit over 68% of the data points are between one standard deviation this way and a standard deviation this way. So 68% of the data falls within one standard deviation of the mean. And this is the mean if we shifted it. And 95% falls, that 95% is all of this, falls between two standard deviations of the mean, and 9.7% approximately falls between three standard deviations of the mean, three standard deviations this way or this way. That really is what the bell-shaped curve is. And so this is a statement of that empirical rule. Now, you're interested in other probabilities than just these, and you might say, how do we end up doing these? Well, what we're doing is we are evaluating, and so demonstrating this empirical rule, and actually doing any normal distribution problems involve using numerical integration, because this is not and does not have an elementary antiderivative. And there are whole statistical tables that are made of these. And these statistical tables usually are about the mean of 0 and the standard deviation of 1, because we call that the standard normal. And we have these tables which we can adjust by means of what's called a z-transform to compute any areas. Now, there's much more in statistics, and engineers should really take a course in this, but for now, understand that you've seen applications of almost everything we have learned in this field. Now I'm going to introduce you to the LSA2 that's due on the 25th by 11:30 p.m. Okay, so here are some facts. Given that the duration of a full-term human pregnancy is normally distributed with a mean of 268 days and a standard deviation of 15 days, this is your assumption. I'm telling you this is something that we know in the problem. I'm asking you to use numerical integration and the trapezoidal rule to approximate to the nearest 10th thousandths the probability of a pregnancy being between 260 days and 275 days. So this is number 1. Number 2, I'm asking you, what is the minimum number in of trapezoids you need to calculate this using the trapezoidal rule for the given accuracy? These are going to be put in the answer sheet as before. We're also going to upload a PDF. We're learning how to do another thing you're going to have to do for the final assessment. So you're going to be uploading a PDF of an Excel spreadsheet. You see, these trapezoidal rules are really done best in something like Excel. So I'm suggesting you upload the PDF of an Excel spreadsheet of your work to the PDF upload section in Blackboard. So 3 questions. This is LSA2, and it deals with things that were introduced here and some of the things we learned in the videos dealing with numerical integration. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless each and every one of you.